All right, welcome to the Economic Geology of Lunar and Asteroid Resources. Sorry, it took a few minutes longer than I expected to get set up, but that's the way these things work. My name is Dan Britt. I'm at the University of Central Florida. This is being sponsored by the Center for Lunar and Asteroid Surface Science, along with several other co-sponsors that we're going to get into in a few minutes. But basically, the story of why we're here is that the geology of extraterrestrial objects is fundamentally different than terrestrial geology. And we're entering a period where economic geology is going to be very important to resources. There's planets and asteroids are basically large physics experiments, and chemistry experiments and biology experiments. And it's those differences in chemistry, energy, size, processes that are going to produce much different geological results. So mineral assemblages on these things are going to evolve given the physics and the chemistry and also the biology of each of these objects. So the Earth has something like 4,500 different minerals. Asteroids actually have less than about 100. The moon has about 350. It's not that there is an economic value here, it's just that the geological rules are going to be different. And the whole point of this seminar and these lectures is to dive into the differences in these rules. So basically the focus here is economic geology. Just the geology necessary to understand and exploit the resource that is out in the asteroid belt or on the moon. And the core content is going to be a bunch of topic focused lectures given by leaders in the field. We're going to start out by the differences between terrestrial and extraterrestrial economic geology. Then go into lunar geology, asteroid geology, and some other resource issues. I do have a schedule correction. I forgot about the university holiday on January 13th. So the January 13th lecture will be given on Wednesday, January 15th. The discussion session for Wednesday the 8th, which people in this room are required to show up for, will not be on Zoom, and we'll be just talking about class organization and assignments.
I think the holiday is on
The 20th?
Yes, MLK Day is
The 20th, okay. My mistake. Really?
Yeah.
Oh, damn. Okay, so there will be a lecture on the 13th. Never mind. But I will move the 20th lecture around. Ah, that's terrible.
Yeah.
Anyway, so let's go back to class mechanics. So all participants are encouraged to ask questions. Real-time participants can use the Zoom chat box and ask questions, and that will be monitored, and the questions will be relayed. A lot of the lectures will be, by necessity, accessed remotely via recordings. And so all the speakers will have contact information, or if you don't have contact information from the speaker, you can send me an email, and I will contact the speaker to get a question through. Of course, the course website and the password are available. The website has suggested readings for each lecture, a brief biography of the speaker, links. Just remember that it'll take a few days for the link for each recorded session to be on the website. This is being brought to you by CLASS. What is CLASS? It's a NASA-funded institute to address basic and applied scientific questions fundamental to exploration. It's part of the NASA Solar System Exploration Virtual Institute, SSERVI. The whole idea is to attack exploration issues associated with the new space economy with the best science talent in the world. And and access to the best science talent helps you explore smarter, safer, and cheaper. CLASS is a collection of scientists and engineers from 4 NASA centers, 16 universities, 14 new space companies, 5 observatories and research centers. And we do a bunch of things. We provide high mineralogical fidelity regular simulants in the Exolith lab. We bring together the best talent for looking at asteroid, exhaust plumes and landing issues with airless bodies in the CLASS landing team. And we also do these seminars to provide professional education and bring the right science insights to bear on exploration issues. Our partners in this seminar are CERVI, the Center for Lunar Science and Exploration at the Lunar and Planetary Institute associated with the Johnson Space Center, and also the Florida Space Institute. So let's get back to why we're here. How is economic geology in asteroids and the moon different than economic geology on the Earth? And that's fundamentally remember, we're talking about economic geology. So an ore is essentially the critical thing in economic geology. It's something that you can extract that has economic value, and you can make a reasonable profit. So that's not a physical or geological concept. It's really an economic concept. And it depends on a lot of factors that impinge on geology. In terrestrial geology, an ore usually implies some sort of concentration mechanism. Either usually igneous, sedimentary, or hydrothermal. The fundamental difference in planetary geology is these concentration mechanisms can be either very different or completely non-existent. You can still have an ore without concentration mechanisms, but you have to recognize that none of these concentration methods are going to be operating on other planets. The other factor that I should remind the students in this room is that it's part of your assignment to ask questions. So if you have questions or insights, or you just want to think that I'm totally off base, you need to speak up, because part of the seminar is to learn to make comments. Yes?
So extracting helium from the surface of the moon would be an ore?
The question is, extracting helium from the surface of the moon an ore? Absolutely, as long as you can make money doing it. And and plug into the worldwide helium-3 market.
This is Jeff Planet.
Probably needs to exist. Anyway, and keep an eye on the chat box, if you would.
Yeah, I have a quick question or comment. This
One
is
of
Jeff
you
Planet.
has volunteered to help out with the telecom. Is it you? Yes. Okay. So, anyway, to move along, okay, so if you could advance that one. So, an example is platinum. The average crustal abundance of platinum is 0.005 parts per million. The way I think of a part per million is that that's 1 gram per ton of whatever it is. So the average crustal abundance of platinum is very small. In the Marinsky Reef, which is in South Africa, and that's what this, excuse me, this picture is of. As you can tell, there's some weeds here for scale. That's 75% of the world's platinum reserves right there. These little veins horizons of black rock. The abundance there is about 10 parts per million. That's a concentration factor of 200 or 2,000. So a huge amount of concentration. And basically what's happened is that process has scavenged rock over a huge area, scavenged the elements in those rocks and concentrated them in these narrow horizons. And that's typically what you get in economic geology. Why isn't this advancing? Okay. Concentration is the key to economic geology. So most economic minerals need to be concentrated. And even concentrated ores have a huge amount of waste rock. This right here is an 860 kilogram block of gold ore. And that's the 30 grams of gold that can be extracted from that ore. And that's actually a really good ore. And so concentration factors for various things to make it an ore are on the order of thousands, for instance, in lead, 2,500 or 500 for uranium. And this varies depending upon economics. If the price goes up or down, the concentration factor necessary for an economic resource goes up or down. Did that one advance? Okay, good. So the terrestrial concentration process, briefly, is essentially a function of source materials. This is typically a finely disseminated elements or minerals at very low abundance through a huge amount of rock. And it's liberated by some process, usually involving fluids. Those same fluids mobilize the rock and transport it. And then you need a trapping mechanism that concentrates that resource. Quite often the trapping mechanism is variations in heat and pressure as the fluids move through the rock column. But fundamentally, this requires fluids, heat, high lithostatic pressures, and lots of time. And the result is this highly concentrated stuff that we call ores. In asteroids, you don't get that. Asteroids had one heating cycle back in the very early solar system at 4.5 billion years, one and done. You had essentially a combination of a low temperature aqueous alteration where you took assemblages of olivine, you cooked them in water, turned them into essentially clays, muds, and locked some of that water in the phyllosilicates. You had high temperature complete melting where you took a chondritic assembly and melted all that down so that the silicates floated to the top, the heavy metals dropped to the bottom, and you ended up with iron cores. Subsequent impacts stripped the iron cores, exposed them, iron cores got fractured. We have iron meteorites that are pieces of the cores, and obviously since you're holding the core of that object in your hand, that object doesn't exist anymore. But the resource there is massive iron and massive iron-loving elements, siderophile elements. In that disseminated in that material. So we'll have a whole lecture on early accretion and evolution of asteroids and how this process happened. Question. What are siderophile elements? I'll have a slide on that. Terrestrial processes are typically driven by plate tectonics. This is a diagram of the distribution of copper mines. And if you want to look at current or past continental collisions, you just look at the distribution of these things because they're driven by continental collision processes. The whole idea is continental collisions provide the energy, the fluids, the heat, the pressure for these things. Did you advance that one? and the faulting. So the sources, the transportation, and the traps for this kind of mineralization. Yeah. Almost all of these things are messing up now. But you're not in the copper belt anymore. On the moon and asteroids, there's no plate collisions, plate tectonics, no continental collision, low lithostatic pressures, no available fluids after the very early days, low to no internal heat flow, no hydrothermal systems. Concentration factors and processes are fundamentally different. So the terrestrial process results in highly localized ore bodies. Typically what you've got is small, high concentrations of stuff surrounded by lots of, from an economic point of view, waste rock. These are in discrete pods or veins or zones of enrichment. And the exploration process is a process of localizing the resource with finer and finer knowledge of the site. The better and denser the exploration and modeling, the less rock you have to move to get at the resource. In contrast, small asteroids are typically a single mineral assemblage. We have 4 independent lines of evidence that tell us that. We've rendezvoused with 4 small asteroids. All of them are a single mineral assemblage. They're different mineral assemblages. Eros and Itokawa ordinary chondrites. Ryugu and Bennu are carbonaceous chondrites. But there's essentially no variation from an economic point of view in any of these guys. We have other lines of evidence, rotational spectroscopy, meteorites and meteorite showers, and also the spectroscopy of asteroid dynamical families. You just don't see huge mineralogical differences across these things. Yeah.
I'm sorry, could you explain what a chondrite is?
Good question. What is a chondrite? A chondrite is basically the sand of the solar system. It is what all the planets, all the terrestrial planets are essentially made of. And so a chondrite is 3 major things: olivine, pyroxene, and iron. And so olivine and pyroxene make up the mantle and the crust of terrestrial planets. The iron makes up the cores. And almost everything is derived from chondrites. So for small asteroids, one of the major potential resources is water. You can find the water in hydrated minerals on volatile-rich carbonaceous chondrites. Examples of this are Bennu and Ryugu, where we have Japanese have a rendezvous mission with Ryugu right now. NASA is running a rendezvous mission with Bennu. How do we know these things are volatile rich? Well, we have samples. We have 900 volatile rich meteorites in our collections. So it's not like we're ignorant of their mineralogy. The diagram here shows the mineralogy of a collection of CM carbonaceous chondrites. These things are typically about 80% phyllosilicates, which have structural water in the crystal structure of the mineral. But this is a fine-grained mineral assemblage that's intimately mixed. So in addition to the phyllosilicates, you have 20% of things that aren't volatile rich, but they're mixed at the micron level. So there's no concentration mechanism. The entire asteroid would be the resource if you're after water, but you're not going to be able to separate out the olivine from the phyllosilicate because that's mixed at the micron level. Where to find water? Well, you look at the water content of these guys, volatile rich carbonaceous chondrites, and you get something like 15 or 20% water. locked in the minerals. The rest of these meteorites are going to be rocks. And that's just to reiterate the mineralogy a little bit. Various ones of these are 80% alteration minerals. And that's what you want. That's your resource. Again, no concentration. But we know this because we have 900 samples of these guys. It's not like we're ignorant of these data. Metallic asteroids, remember these are fragments of cores. They melted and differentiated in about the first million years after accretion. And so they've concentrated siderophile and chalcophile elements in the cores. And I will explain those terms in the next slide. But how do we know this? We have over 1,200 samples of iron meteorites. And this beautiful pattern is called the Widmanstätten pattern. That's evidence of very slow cooling, essentially at the core of a small planet. Whatever concentration that is in these things occurred during formation, occurred 4.5 billion years ago. And again, the entire asteroid is a resource because all your interesting stuff is disseminated in this material. Question?
Did you want to know when like the chat was happening? Wanted me to check that?
Yeah, if you would.
There is someone.
Okay, but they haven't finished typing yet.
Gotcha.
Okay, well, just let me know when the question comes up.
Okay.
All right. Siderophile and chalcophile. So the red is siderophile, the gold, actually yellow is chalcophile. Siderophile are just iron-loving elements, elements that combine very easily and tend to stick together with and dissolve readily in iron. So things like platinum group elements are siderophile. Chalcophile elements are things that combine readily with sulfur. So things like copper and silver are chalcophile. And both chalcophile and siderophile elements are enriched in asteroid cores. I wish this thing would work consistently. And how do we know this? Well, remember, 1,200 samples. So you can analyze these things in great detail. This is a bunch of analyses of various meteorite groups. And over here, platinum group elements like gold. And this is parts per million, again. So for many of these types, you have somewhere between 3 and 12 parts per million or grams per ton of platinum. Question?
So wouldn't it be easier to separate these discrete metals in an iron meteorite though than like to separate out the water from the phyllosilicates?
It depends upon what you're after, of course.
Okay. Well,
So the question is, wouldn't it be easier to separate out elements from iron meteorites versus water from
because you know, could
phyllosilicates?
you theoretically melt it and it will just separate by density?
Well, yes, but there are lots of complications involved in that. And phyllosilicates are actually not very strong crystal structures.
Yeah.
So it's relatively easy to get water out of the phyllosilicates. Separating out 3 parts in a million of platinum out of iron might be fairly challenging.
Just need to
But-
put enough vat.
Well, yeah, just need a big enough vat. Yeah, well,
It looks like there are some questions.
sure.
in the chat.
So if you would, okay.
I'm not seeing any question. I'm mostly seeing comments here and there.
Okay, well, let me know what the comments are.
Yeah, from Jeff Plate, he says, without concentration, I doubt asteroids qualify as ores due to the lack of economic viability.
Well, economic viability, that's a good comment. Economic viability is not a geology question. It's a finance and organization question. People have talked about mining asteroids for water. The major qualification on being an ore is a financial one rather than geologic one. And the whole point of this class is to clarify the geologic realities. And that's what I hope I can do over the next 3 months. And it's still not advancing. All my toys have failed me. So a few definitions. Basically, in the field of economic geology, there are a lot of precise definitions because money is at stake. This is not just getting tenure or getting published. It's getting sued or making lots of money. And so people are very careful about how they define resources because it's not just scientists involved. It's a lot of other people who have a lot at stake. And so a resource is a concentration of minerals that has reasonable prospects for economic extraction. And you go all the way down this list. I'm not going to read them all. But what you want to do is get to a proven mineral reserve, an economically mineable part of a measured resource. And the whole point of this exercise is to move from a resource to a reserve. And there are fairly standard ways of doing that in terrestrial geology, which is why they have all these. Boy. Next one.
There we go.
The process of turning a resource into a reserve is essentially increasing knowledge of the geology and increasing localization of the ore zones. Since the ore zones are very discrete and very concentrated, and everything else around this is a waste of time from the resource point of view. What you want to do is you want to increase your knowledge from things that are inferred when you know the basic geology to indicated to finally measured, and you go from probable to proving this. And the process is designed basically with the assumption of a highly localized ore body surrounded by a lot of waste rock and overburden. Because when you're mining this stuff, you tear off, you either mine down through the ore horizon or you tear off the overburden and just scoop it out, depending on what the economics are. So this can be understood as a probability distribution. When you start out, you're down here at low probability, but you think that there's a lot of stuff. And as you learn more about the resource, you increase the probability of a certain amount of resource being available. And you also learn the other factors, excuse me, recovery factors, economic factors, social factors, governmental factors, tax factors, that finally gets you to a curve where you have an economically recoverable reserve, a certain amount at very high confidence. And economic here is the key term. The calculus is not just geological, it's financial, environmental, regulatory, legal, governmental, many others. And it depends upon how much money you're willing to spend on obtaining that knowledge. Asteroids are going to be fundamentally different. It's still a probability of distribution, but since the entire body is the ore, the localization imperative is irrelevant. Resource identification on asteroids is more likely to be a step function than a curve of increasing knowledge. You know meteorite mineralogy. You have remote sensing to identify high probability asteroids. And the remote sensing can tell you the meteorite analog, the mineralogy, the size, the mass, the physical properties, the rotation state. and fundamentally the resource potential. So you get an idea about how big the asteroid is, how much of the resource is actually there. And then your last function is to verify that, essentially with in situ analysis, either sample return or remote in situ measurements to verify the mineralogy. And boom, you're at 100%. And I have a step function going down to a smaller resource, but the step function could go out. Because once you go to that asteroid, you can discover, oops, it's bigger than we thought, rather than oops, it's smaller than we thought. So the lack of concentration process means that you don't want to do things like high grading or traditional localization surveys because they're irrelevant. So for the resource evaluation, moving this resource to a reserve, economic geology actually has a system of progressive steps. And the asteroid equivalent is going to be different. In the terrestrial process, you collect geological information. In the asteroid equivalent, you would identify the object, its meteorite analog, size, mass, physical properties, rotation state. Terrestrially, you'd build a 3D model or a block model to extrapolate drill data. But since this is a single assemblage, that's not applicable. Determine the resource based on the modeling. Well, based on the meteorite mineralogy and the asteroid mass, you can determine the resource. Then you need to acquire mining, metallurgical, economic information. But in the asteroid case, you do sample return and in situ analysis. And that gives you the ore grade and the reserve to high confidence. Grade and asteroid mass give reserves. And then that goes into a mining feasibility study. Fundamentally, you need to have a lunar and asteroid specific resource evaluation process. So let's talk about the moon a little bit. Basically, the moon was produced by a giant impact that ripped off the crust and some of the mantle of the early Earth. The moon got 2 extra cycles of heating, but the basic mineralogy is going to end up being fundamentally different from the Earth because, again, it doesn't have plate tectonics. It doesn't have the 4.5 billion years of crustal evolution. Dr. David Crane will address the origin and early evolution of the moon and talk about things like the lunar highlands and the magma ocean, which cover 85% of the surface of the moon. Britt will address the geology of the lunar highlands. It's useful to remember that the results of this mineralogical experiment are going to be much different. That lunar basalt does not equal terrestrial basalt. These things are fundamentally different. Lunar basalts are higher in titanium and iron, lower in a lot of other things. And 85% of the lunar surface is an orthosite. So that's going to be much different. Surface processes both on the moon and in asteroids are going to be dominated by impacts. So at all scales, you are saturating surfaces of the moon with impacts and on asteroids. Small asteroids are typically going to be rubble piles bound by gravity and air particle forces. The moon's surface is going to be covered with impact ejecta, sometimes to the depths of thousands of meters. And the impact ejecta that's there will be gardened and will disperse and mix anything in the tens of meters depth. Remember that gardening is going to be affecting these lunar polar deposits, these lunar ice deposits. And gardening will be more intense at older surfaces because this is essentially a time function Longer the time, more the gardening. And so this is going to mix and scatter lunar polar ice. Now, Clive Neal is going to address lunar surface environment. Kevin Cannon is going to talk about polar ice. Next. Let's prospecting on the moon. It turns out with airless bodies, remote sensing works pretty well for a lot of lunar resources. Iron and titanium, and remote sensing and lunar samples have combined to do a great job of mapping iron and titanium on the moon. There are good iron and titanium maps. But by terrestrial standards, the moon is actually a fairly poor resource for titanium and iron. Ore grade titanium on Earth is typically 55% weight TiO2. Iron on the moon is mostly in silicates, and that's actually quite difficult to get at compared to the Earth, where you typically take iron out of hematite and magnetite horizons. And Clive will be talking about the geology of the lunar mare. Next slide. So where you need local prospecting is for ice at the poles. We know where the shadowed regions are. Don't you have to get going? Okay. We know where the shadowed regions are, but not much about the distribution or the amount of the ice. Whatever the distribution and amount, it's going to be affected by regolith gardening. And so that's going to mix the stratigraphy and the distribution of the ice. You should not be expecting large coherent ice ore bodies. And so Dr. Cannon will address lunar polar deposits. Next slide. Like asteroids, our prospecting is aided by a substantial collection of lunar samples. The Apollo program brought back 2,200 samples, almost 400 kilograms of rocks. The lunar program from the old Soviet Union provided 300 grams. There's about 400 lunar meteorites, mostly sampling the highlands, for another 200 kilos. So there's plenty of samples. And they tell us all sorts of useful things. This is a plot of aluminum versus titanium. As you can see, if you want titanium, you need to go where Apollo 17 and Apollo 11 went, for the high titanium areas. Almost every other place is about the same. The 7s are Apollo 17, the 1s are Apollo 11. The letters are the Luna sites. This is, the cross right here is the average Earth. All the gray crosses are meteorites. So we have a lot of information. Next slide.
Dan,
Yes.
you have a comment from Jeff Plate again.
Okay.
It says at WGM's Waterworks group, we believe the gardening and thermal flux on the moon act as a mobilizing agent for deposition into cold traps.
Okay. I think good point, and we'll talk about that that more in the future. Does he think it concentrates more resource in the cold traps?
Yes.
Okay. Okay. All right. Good point. More comments?
There was another one about definitions of resources and reserves.
Yeah.
The definitions of resources and reserves on all global standards for mining are based on the terrestrial environment, not an off-world one.
Yes.
Big hole right now.
Yes. I can't agree more. So, one of the things that we'll discuss is that lunar trafficability is an issue. This is something that Dr. Phil Metzger will address, but part of the problem that is not well understood is that prolonged activity seriously degrades lunar soil compaction. What the question?
Sorry, is that kind of like is it like a similar effect to like liquefaction of sand, where like as you step on quicksand, it kind of like sinks you in? Is there a similar thing going on here?
Oh, well, the question is it similar to producing things like quicksand? I'm not a, that's not my field, so you'll have to ask that of Phil. I just relate that what you find is that after a few days, when you've worked this material, it becomes loose and tends to be kind of, it's called a quagmire of material, is what in the high traffic areas.
I guess maybe a better version of my question is like, is there a surface that's being disrupted and that's like revealing the loose fluffy stuff, or is it the vibrations from walking that's making it be loose fluffy stuff?
Well, I think the question is that what's driving this? Are we breaking up a surface, or are we creating a flux? And I think that would be a useful PhD.
Okay, well, sorry.
I mean, I think so the idea here is that when you have this descent loops, it drives a lot of the superficial layers away, so you're left with a more consolidated surface underneath. But then when you're stepping on it,
It's unconsolidated.
it's more
Yeah.
unconsolidated.
Okay.
Yeah.
So like the lunar surface has lots of layers that are like less cohesive or less consolidated, and then more consolidated. And has this really interesting layered structure.
Yeah.
It's like compacted insulation, and then you're ripping off the top of it, and you're messing with it, so
Sort
it's
of.
getting everywhere.
Yeah.
Like powdered sugar.
Well,
I know.
again, I just mentioned this as an ad for Phil's talk. Phil will also be talking about the issues with landings and takeoff, which accelerate this otherwise innocuous dust into high velocity ejecta that could be bad for anybody in the neighborhood. And the neighborhood expands to distant retrograde orbits. So, also trafficability affects a lot of things. If you're going to be mining the ice, remember that the ice is holding up the surface. And so mining will cause terrain collapse. It's worth remembering that a common feature in rural areas are things like sunken lanes. And these lanes didn't get sunken because people excavated them. It's just repeated traffic compacted that material and caused the road to sink relative to the fields. And that might be another feature of lunar trafficability. Question?
Question in the chat from Jeff. Is this due to the clay-like nature of the phyllosilicates and their flat geometry?
Question is it, my answer is that save it for Phil. This is not my field, so I'm essentially advertising for him, but that's a good point and a good question. And it's one of the many things I do not know. Next slide. So remote sensing also works pretty well on asteroids. Water-rich asteroids and water-rich meteorites are way darker than water-poor asteroids. Fundamentally, you just need to look at albedo and you have a pretty good indication that the thing is water-rich. Metallic asteroids have high radar albedo. So, and then once there, you don't need to prospect on the small asteroid. Again, ores aren't concentrated, no concentration processes. You don't get significant mineralogical variation. So the whole thing is an ore body. You don't high grade it. You don't need to cridge it. You just start to mine it. And I will talk about prospecting in detail in a later lecture. Next slide. So to wrap up, I apologize for all my equipment failures here, and I'll figure out why these things are not working correctly. But mineral evolution and geology are fundamentally different on the moon and the asteroids and the Earth. The geological concentration mechanisms that we base our concepts of economic geology terrestrially do not exist on the moon and asteroids. You don't have these processes like plate tectonics, heat flow, available fluids, hydrothermal systems. Useful asteroids contain volatiles and metal, the rest are rocks. Prospecting for ore asteroids probably can be done very well remotely. Small asteroids are overwhelmingly a single mineral assemblage. Once at the asteroid, don't waste your time high grading. Next slide. Regolith processes produce interesting results and need to be kept in mind at all levels when you're dealing with lunar and asteroid resources. Remote sensing works pretty well on the moon for some things like iron and titanium. But an ore is an economic concept, so everything depends on cost. You need to reevaluate your mineral evaluation and resource standards for the realities of lunar and asteroid geology. Ore geology on the moon and asteroids is different, but very understandable given the knowledge and given knowledge of the geologic context. Just have to keep in mind the environment and the geologic history. And of course, that's the objective for the course. So I thank you and open it up to more questions. And more questions online.
I'll ask a question because I like talking.
Okay.
So, do you think that like strategic mineral reserves are also going to play an impact in like determining the economic feasibility? Like you were talking about earlier, that most of the world's platinum is in South Africa. If for some reason a bunch of countries wanted to put like an economic embargo on South Africa, that wouldn't necessarily work because we get platinum that we need for certain like electrical components from there. So do you see that that might have a very big impact on asteroid mining?
Probably not. And the reason I say probably not is that that's far enough in the future. And also the reason that the reserves are in South Africa is that's the most accessible and easily mineable. There are a lot of other potential platinum reserves that are more expensive and more difficult, or the environmental issues are more extreme. So in the short term, it's difficult to get more resource, but in the long term, there's a lot of other available resources on Earth. So I wouldn't worry about that too much. So I'm not worried too much about the strategic aspect of it.
I'll ask a follow-up question then. Do you see the primary economic use of asteroid mining to be supporting off-world anything like colonization, in situ resource utilization? That's kind of what the majority of it will be used for.
The question is the use of extraterrestrial resources mostly going to be extraterrestrial? And I would say yes. But again, what you use this stuff for is an economic and not a geology question. So I won't be going into much depth about that. Question, in this class you talk about the economics of overburden at the lunar poles and buried ice. How deep of dry regolith is too deep economically? I don't know. Again, that is a question about not just the geology, but also the economics of that particular recovery. And that's, I don't have much to say about that. You wouldn't bring things back to Earth in the near term. As a CEO of a lunar mining company, Interstellar Mining, I look at it only at the economics of this. So yeah, you would be mostly doing extraterrestrial stuff. Is lower gravity going to help or cause more problems? We're actually going to have a lecture about that by Addie Dove, who just left the room. Yes, I think that lower gravity will help quite a bit. The problem is that almost all mining equipment right now is designed to use gravity. And so, as Jeff says, the short answer is both. I think clever designs and using the material properties will probably make it a benefit in the future, but you're going to have to design material to, or design equipment to take advantage of those issues. Let me check for more comments. Okay.
Hey, Dan,
Yes, question.
I have a question. So obviously we have a lot of remote sensing data of the moon.
Yes.
But we mentioned our actual samples that we have. So you said we had about 2,700 and the Apollo samples were 2,200 of those.
Correct.
Is that a good sampling or is that mostly just sampling like the creep?
Well, the question is, are our samples a good sampling of the moon? And the short answer is no. What drove the Apollo program and the Luna program are places that were easy to get to. And they got bolder as they got more experience. But the hardware was limited to a equatorial belt simply because you didn't have the energy to go to higher or lower latitudes. And so it turned out to be a fairly unrepresentative part of the moon. As I said, 85% of the moon is Highlands terrain, and we basically had one Highlands mission. That said, it might be that they found the most interesting, geochemically interesting terrain by serendipity. But now that we've remote sensed the moon a lot more, we've been putting that data into a larger context.
There is an entire suite of lunar meteorites that are random.
Yeah, and the 400 odd lunar meteorites are a random sampling of the surface. And what you see is that you get way lower titanium on almost all the lunar meteorites because they're dominantly coming from Highlands terrains. More questions?
Yeah, Dan, you have a few questions.
Sure, if you'd read them.
Well, from Bryn and Sarah in the room.
Oh, okay.
You said the prospecting for small asteroids was fairly simple with remote sensing. What's different about large asteroids that makes them harder to remote sense?
The question is, what's different about large asteroids than small asteroids? The issue, actually, large asteroids are easier to remote sense than small asteroids. It's just that small asteroids are the ones that are accessible in nearer space. You just don't get big asteroids in nearer space. They're in the asteroid belt. What we've seen with big and we've orbited two big asteroids, Ceres and Vesta. And you were about to make a comment?
I was going to say, what's the working definition here of large and small asteroids?
What's the working definition of?
Small asteroid in this
Pardon me?
case? Is Bennu a small asteroid in this case?
The working definition of a small asteroid is basically anything, any asteroid in near space. Smaller than a few kilometers, 10 kilometers. And so Bennu and Ryugu are small asteroids. And our knowledge of small asteroids is not great, but it's pretty good. And what we've seen so far, since we've rendezvoused with 4 small asteroids, is they tend to be single mineral assemblages. Very, very much like you see in the meteorite collection. Okay, go ahead.
I know like the waste rock isn't really a concern mining an asteroid, but what are some of the waste or debris? Like, what do you have to clean up if you're going?
The question is, what do you have to clean up if you're mining asteroids? That's a good question. And when you're extracting water from phyllosilicates, remember that 20% of the asteroid is not going to have any water. And then 80% of the phyllosilicate is not going to be water. So all of that will become waste rock in some fashion. And essentially what you're doing is you're smashing those crystal structures and pulling out the water. So you're ending up with essentially the structure that you had originally, which was more like olivine, except you're not, essentially you're creating glass. So essentially you're going to create kind of a dust pile of amorphous silicates. And then you have to ask yourself, is that good or bad? But that's not a question I'm going to ask. And I'm not going to do the good, bad questions in this class. Let me check the chat real quick. Will there be any discussion of economics of extraction of oxygen from regoliths, such as the titanium and iron-bearing minerals you mentioned earlier? And the answer is yes, but that will be later on. And let's see. Why is the mineralogy of the moon so different than the Earth's? Why do we have to consider the moon as kind of a daughter of the Earth? Is it because of the lack of tectonics? Well, yes. The fundamental thing with the Earth is that we live in a very reactive and unusual chemical and physical environment. We have tectonics, but we also have abundant water, oxygen. All of those things react to form different minerals. That kind of heat, pressure, and chemistry is just not available on the moon. You have a different kind of chemistry in the lunar case, but it just does not produce the same kind of diversity of minerals that you get on the surface of the Earth. And you simply don't, the nice thing about the diversity of minerals on the Earth and the chemistry and the continental collisions is that they have it, is they provide these concentration processes which create economic minerals. So a lack of tectonics, a lack of water, a lack of an atmosphere, all of that restricts the amount of mineral evolution that you're going to get. And I will talk next week on Monday about mineral evolution. Question, would there typically be some correlation between particle size and mineral composition for asteroid regolith? Probably not. The phyllosilicate-rich asteroids that we're talking about tend to have fairly fine particle sizes to begin with. And you don't, things that are slightly bigger particle sizes tend to be relic chondrules, which also tend to be volatile pore. So, so partially yes, but I doubt that that has much effect. Particle size and composition for lunar regolith, I'll have to defer to Clive Neal and Dave Kring on that. Questions here? Yeah.
So I don't know much about how mining really operates, but on a really low surface gravity object, something that we're talking about is less than 10 kilometers, what's like the escape velocity of that? If I hit the surface with a hammer, is that stuff being ejected, or?
The question is, what's the escape velocity for a small asteroid? Tiny. So if you're mining on a small asteroid and you hit a rock with a hammer, you probably accelerate to escape velocity.
So this stuff probably has to be contained, right? Otherwise you're just
Well,
using-
hammers are not, the question is, does the stuff have to be contained? And I think the answer is that the hammers are probably not the best tools for this kind of operation.
So most concepts also bag encapsulate higher asteroid.
Yeah, comment here is that most mining concepts on asteroids talk about using a bag that encapsulates what you're mining.
And then do you take it to a body with gravity to process it?
The question is, do you take it with a body with gravity to process it? No. What you can do is cook it. There's one concept which uses solar concentrators. And essentially you cook the whole thing through with solar concentrators, essentially peeling off a bit at a time. And the bag traps the volatiles and concentrates them in a cold trap and process it. An actual bag.
What's the timescale for cooking an asteroid?
So the question is, what's the time scale for cooking an asteroid? And it depends upon how much energy you have available. It turns out that there's quite a bit of solar energy available, and a solar concentrator can blast through a small asteroid pretty fast, small being tens of meters. And there's a fair amount of water there. Question?
So with the OSIRIS-REx mission, with the new, since it's such a small asteroid, and with the sample collection, is there any concern that, like, when you collect the sample, like blasting the nitrogen on the surface, it's actually going to be able to collect enough of the regolith to bring back for the sample?
The question is the way that the OSIRIS-REx mission is collecting their sample. Are they concerned that they will not be able to collect enough?
Like, will it eject too quickly or whatever?
I'm sure they're always concerned about that. I don't know. I'm not involved in the mission, so I think that would be a good Umberto Campine's question. Do we know what kind of ore on the moon is valuable currently? Is it possible that something is waste now will be useful in the future? That's an issue constantly in mining. There are lots of operations that mine spoil piles of previous mines. And again, all of these things, value is subjective. It's a function of economics, not of geology. And so things that you throw away today, you might discover a highly valuable use for in the future. Jeff Plate says, water and valuables for now. You need a lot of infrastructure to mine metals on the moon, which is so true. The only problem is the amount of and composition of the volatiles in water are not very well known yet. And that's certainly true. We'll talk about that and talk about what is known and what can be guessed and what we'll have to go find out. And there's a lot of to be found out. Yeah, so, and operating on the polar regions is not trivial. And we'll talk about how you operate on these regions in the moon and what we know about that. More questions? Yes.
When you talked about the bag trapping the water, what would that water be used for?
Well, the question is, what would the water be used for in any of these things? You can use the water for fuel. There are a couple of ways of doing this. You can electrolyze the water and separate it out into oxygen and hydrogen and use that as a high specific impulse power. Or you can there are thrusters that just use water now. Essentially use water and microwaves to break to accelerate the molecules and use them for thrust. Also, water can be used for life support, for shielding. Water is a very useful thing. So if you can get large amounts of it and don't have to drag it off the surface of a deep gravity well, like this one, there's economic value there.
What is the current price for a gallon of water in orbit around the moon? Like $22,000?
What's the current price of a gallon of water around the moon? I don't know. But typically it would be a liter of water. And
You're probably right about it. Sorry.
Yeah.
Jeff just responded, 10 million US dollars per ton for water on the moon.
okay, so, all right, 10 million a ton.
And then there was a question that kind of got lost that brought back up to the front. Dan, if you didn't see
Okay, what, can you read that to me?
that. Does the asteroid, I do not know how to say that.
Apophis, have any
Apophis.
useful resources we know of? It's coming really close to the Earth in 2029, maybe an easy chance to get on a near-Earth asteroid with mining infrastructure. I don't offhand know what the spectral type of Apophis is. I will look into that and find out. Let you know in a future lecture. But typically what you'd want in mining asteroids is you want to find an asteroid that's in a long, roughly the same orbit as the Earth, but in what's called a long synodic period. That is, that it's approaching or receding from the Earth slowly and relatively close in nearest space. And that way you can not only get to it fast, but you can continue to communicate with it and bring off resources relatively cheaply. I think the Apophis, I'd have to look at what its period is and its orbit. Pardon me? It's an S-type, yeah. So Kevin says Apophis is an S-type, so it will have like 15 weight% iron, nickel, but it won't have any volatiles. It's essentially a rock. So more questions over here. Okay, more questions from the online audience. Well, thank you all for attending. And we'll be back online on Monday with a lecture on mineral evolution. And if you have any questions, certainly send me an email at dbritt@ucf.edu. And I thank you very much.